In this chapter, we're going to look at two facets of a chemical reaction: energy changes and the reaction rate, or how fast a reaction goes. We have questions like, why do some reactions, like the gasoline in your automobile, release energy to make the automobile go, and other reactions like photosynthesis require energy? For example, it takes chlorophyll and carbon dioxide and water plus energy to make glucose and oxygen. We also might think, why do some reactions go very, very quickly and other reactions take a longer time to proceed? Well, to answer these questions and understand the concepts around them, we have to look at the molecules. And we have to think about the molecules and when they come together in a reaction, what type of energy is needed to break bonds and released when they form bonds. So we have to go down to things that are very, very small to understand these big picture questions. But let's begin with energy. Energy, the definition of energy is it's the capacity to do work. So right there, energy is the capacity to do work. And when we talk about energy, we can divide it into two big categories. There's kinetic energy, and kinetic energy is the energy of motion. So anything that's moving. So when you throw a ball and it goes through the air, the ball has kinetic energy. And if you're in a car driving down the freeway, you have kinetic energy. If you're a skier on a slope going down the mountain like they did in the Winter Olympics, you have kinetic energy. So anything that has motion has kinetic energy, including molecules. So when molecules are moving, they have kinetic energy. The second type of energy is potential energy. Now, potential energy really has two sources, or you can think about it in two ways. Potential energy in general is what we call stored energy. And you can see here there's two places energies we consider stored. One is in the chemical bonds. So for example, gasoline, if I had a gallon of gasoline and I sit it on the counter, I don't really think of it as having energy per se, but I know that if I put it into my automobile or my lawnmower, that the reaction that occurs will release energy. That's because the gasoline and the chemicals have energy stored inside their bonds. And when we break those bonds, the energy is released. So another example of potential energy that's chemical would be like your food. So we have an apple on the counter. That apple has potential energy. The energy is released when I eat it, and it goes through the chemical process of digestion. So that's potential energy that's considered chemical energy because it's in the bonds. The second type of potential energy depends on the position of an object. So if I'm on the top of a ladder or at the top of the stairs, I have potential energy. For example, I could jump off or fall off, and then my potential energy, because I'm above the ground, would turn into kinetic energy. So, which brings up the next idea, or brings up an idea about energy, is that energy forms can be transferred from one type into the other. So things like kinetic energy can be transferred into potential energy, and potential energy could be transferred into kinetic. So you'll have to use your imagination because you can't see me here, but let's say I put something on the top of a ladder. I take and I place a ball on the top of the ladder. It has potential energy. If I knock the ball off, the ball will drop to the ground, and as it's dropping to the ground, the potential energy is changing into kinetic energy. If I wanted to pick that ball back up and put it on the top of the ladder, I have to use my energy, my kinetic energy, to replace it to get it to have the potential energy again. So kinetic and potential energy can go from one to the other, and that ball, by being on the top of the ladder, has energy that's related to its position, that's potential energy. So examples you might see in your book are like if you're the skier and you're at the top of the slope before you go down, you have potential energy. If you have a waterfall, the water at the top of the before it goes over the edge of the waterfall, that would have potential energy. Anything that's really above the ground there that is going to have potential energy based on its position. Now, there's natural laws. We learned about the law of conservation of mass, which says that matter cannot be created or destroyed in a chemical reaction. The law of conservation of energy is along the same lines. It's a natural law, and it says energy cannot be created or destroyed, although we know it can be converted from one form to another. So even the generation of electricity just doesn't magically form. There's an energy source such as the combustion of coal or maybe a nuclear source. That runs what we call turbines, which turns steam. It heats water and turns the water to steam actually, and then runs the turbines, and then that can go to create electricity. It's a process of converting one form of energy to another. And once the electricity reaches our house, we might even use it to convert it to other types of energy, like light energy. So energy, the total amount of energy remains the same, but we can convert one form of energy into another. Now, when we're thinking about reactions, one thing, and we'll bring this up later, but it was mentioned in your book in this particular section, and that is that a compound with lower potential energy is more stable than a compound with higher potential energy. So what it's telling you is that chemicals try to reach a lower state of potential energy so that they have less stored energy. So the less stored energy you have, the more stable. The more stored energy you have, the less stable. Now, energy has some units that we haven't been introduced to yet. So looking here, here's the units for our energy. We have units of calories and joules. So, and we could put calories in front, kilo in front of it. So there's one thing I want to show you. So calories, I'll write it over here for emphasis. So calories are just like written like food calories. However, when we're talking about in a chemical reaction, the abbreviation is a lowercase c. Okay, I'll explain in a minute. A kilocalorie, it means 1,000, right? That's what kilo means. So if I have a kilocalories, that would be 1,000 of the little calories. So 1 kilocalorie would equal 1,000 calories. And again, notice that I'm using a lowercase c. Now the other unit that we have, the common unit, there's other units for energy, but these are the units that we'll be using. The other unit is joules, spelled like this, and the abbreviation for joules is a capital J. If we wanted a kilojoule, remember, kilo means 1,000. So if I have kilo there, that simply means 1,000 joules. And we do have a relationship, which you don't need to memorize, between the two units. 1 calorie is 4.184 joules. So joules are actually a smaller, in terms of increments, units than calories. Now when we think about calories, at least I do, I think about food. And so I want to make the distinction that a nutritional calorie, while related to the calories we'll be talking about, is actually an increment of the lowercase c. So let's look. One thing you'll notice in the notes, a nutritional calorie has a capital C when you are abbreviating it. So I want you to go in your house and look at one of the nutritional labels and notice that when it says calories, it's a capital C. And the relationship is right here. So 1 nutritional calorie is actually 1,000 calories. I'll write it up here as well. So a nutritional calorie with a capital C is equal to 1,000 of the lowercase c. It's a little confusing, but don't make it more confusing than it is. It's just a nutritional calorie equals 1,000 of the calories that we're talking about, and which 1,000 means kilo, so that would be 1 kilocalorie. Okay, so a capital C, it makes a difference if you have a capital C or a lowercase c. And we'll talk about this little table right here in one of the problems because it's kind of fun. We're going to do a problem with nutritional calories in a couple slides. So the first thing I would like to do is just to practice converting between the relationships between the units of calories and joules. So on this first problem, it has joules and calories. And the relationship is 1 calorie equals 4.184 joules. So this is a conversion problem like we did in a previous chapter. You write down what you're given, and anytime two things are equal, remember we can write them as a fraction, and we'll put the unit that we're trying to cancel or that we were given on the bottom. So 4.184 joules on the bottom, and then the other side, the 1 calorie on the top. The joules cancel, and then dividing 42 by 4.184, we get 10.0382. This is going to be calories. And if I was rounding, I think I would go to 2 significant figures. So I would just put 10, and I'd put the decimal there to show. So 10 calories. You could also write it in scientific notation, which would be 1.0 times 10 to the 1 calories, but I don't know that that would be required. So now let's look at the second example. So this has kilocalories and calories. So kilo means 1,000. So 1 kilocalorie, kilo means 1,000, equals 1,000 calories. So I have 55.6 kilocalories. That's what I was given. Now I'm going to set up the conversion, and since I was given kilocalories, I'll put it on the bottom so it will cancel. And then I put 1,000 calories on the top. The kilocalories cancel out, and 55.6 times 1,000 is 55,600 calories. And as long as I don't put a decimal at the end, I still have 3 significant figures, because remember the 2 zeros at the end are not significant. You could, I guess, write this if you wanted to in scientific notation, and it would be 55.6 times 10 to the 4th calories. Although, again, I don't think this would be required, but those two numbers mean the same thing. And the last example, and you do not need to memorize these units. You do need to be able to do a conversion, but you don't need to memorize the relationship between the calories and the joules. So this has calories and then to kilojoules. So I know that 1 calorie equals 4.184 joules. So I can do that first. So I can say 2,000 calories. That's what I was given. I'm going to put the calorie on the bottom, so it will cancel. 4.184 4 joules. And so I would multiply 2,000 times 4.184. And that gives me 8368 joules. And I'm not going to round it yet. Then I know, I'm going to write it over here, I need kilojoules. So I know 1 kilojoule equals 1,000 joules because kilo means 1,000. So I will put the 1,000 joules on the bottom, the 1 kilojoule on the top, so they cancel. And so divided by 1,000, I get 8.368 kilojoules. And since this number here only has one significant figure, I could just write as my final answer 8 kilojoules. I would keep it at 8 because I'm dropping off a 3, which is less than 5, so I wouldn't round up. So there's 3 examples about how to convert between the different units. The conversion process is the same as we've been doing in previous chapters, and you don't need to memorize the relationship between calories and joules. Now, the last thing when we're talking about energy and its units, I want to talk again about those nutritional units. And I always think that this is kind of fun because it's something we can relate to. I want you to see here that on this label, the calories is a capital C, which tells me that's a nutritional calorie. Now, each type of food or each type of molecule gives off or contains a specific amount of energy. And here is the relationship between the category of the compounds and how much energy they have. So both proteins and carbohydrates release 4 calories of energy per gram, but fat releases 9 calories per gram. So if we know the breakdown of the different substances in a sample, we can predict the calories or estimate the calories that would be in that sample. So here's a box that has crackers, and you can see it has nutrition facts. So we have here a serving size will be 1 cup. We'll get about 13 crackers. And here we can look, they've already calculated for us 200. Well, the question is, how do they get that number 200? So let's calculate it ourselves. So we see that the fat right there is 1 gram of fat. So 1 gram of fat, so let's do fat first. There are 9 calories per gram. So the grams cancel, and the fat contributes to the sample 9 calories. Then we have carbohydrates. So the carbohydrates have 42 grams. So 42 grams of carbohydrates in these crackers. Each gram releases 4 calories of energy. So we would take 42 times 4, and that's 168 calories. And then finally, we have the category of proteins, which are 5 grams. So if this cracker has 5 grams of protein, and protein as well as the carbs give 4 calories of energy per gram, and that is 20 calories. So we see the contribution of each category. And if we add up all 3, we get 197 calories. Now if we look at the label again, you see that they have 200. And I think that's because when you look, all of these are to one significant figure. So if we take 197 and round it to one significant figure, we get 200. So maybe that helps you understand just a little bit how when they have the calories they're estimated, it's based on the experimentally how they determine the breakdown of the fat, the carbohydrates, and protein. And that's how they come up with the calories that are in your sample. There's actually direct ways to measure calories in a sample, but for us looking at our labels, this is a good estimate.